Hey everybody, Mr. Decker here. This is going to be lesson 4 in Unit 2 for Foundations of Geometry. In this lesson 4, we're going to be covering more of an introduction to proofs. In this lesson, you should be able to understand how proofs are completed using reasoning and properties. Some of you may have already seen this with the algebra handout that I gave you last week. And we're also going to complete algebraic proofs along with geometry, segment, and angle proofs. Now, the algebraic proofs are not going to be covered in this video specifically because I think with the explanation that you got last week, the majority of you should be able to complete it. Really not too difficult. So let's get started here. So first off, we start off with what is a proof. So just so you know what a proof is a mathematical series of statements and reasonings why those statements are true. So think about it from like, here's this point that you're making, this is the reason why it's true. Here's another point that is based off of the original point, and this is why that one is true. It's essentially just a subsequent series of statements and reasonings proving why something is true. So it's like an argument that you're formulating using logical sense, really. Proofs can be completed in 2-column formats, paragraph format, and as a flow proof. We're not going to get into paragraph and flow proofs in this lesson, but we're just going to really talk about the 2-column proof. So a 2-column proof looks like this, where this is an example of a proof that we're going to solve later on in this video. So see that we have this diagram, DEF, this segment with the points D, E, and F. Given information is right up at the top here. It says E is the midpoint of DF. So that means E is right in the middle. So that would mean that D to E is the same distance as E to F. That's kind of what they're saying here. We know that because that's a definition of a midpoint. But this particular diagram is just meant to kind of expose the 2-column proof format. The left side of a 2-column proof is just where your statements go. So this is where you essentially kind of solve the puzzle or solve the problem out. So like we're given this information and this is what we're trying to prove. So whatever we're trying to prove here should always be the last statement because that's what we're trying to prove. It's our last end goal or last statement. Left side is working the problem out. Right side is where all the reasonings go. So this is where those properties, reasonings that you're going to use to support your statement are shown kind of in the same row. And we're going to talk about that here. The properties that we're going to use are pretty, I guess, well condensed in this particular diagram here, this particular picture. Properties of equality include addition, subtraction, multiplication, division. Distributive property, we'll talk about what all these mean here. If you want to just pause this and take a screenshot or use this to help you solve some of the problems, you can. But we're going to move on, and we're going to kind of explain each one of these real quick. So addition, subtraction, multiplication, and division are really just used. Those properties are used whenever those operations are performed. So if we added a number to both sides of the equation, then that's addition property of equality. If we subtracted, subtraction property. If you multiplied, multiplication, division, division. Distributive property is the one that's used whenever you're multiplying a term inside of parentheses. So like you're going to distribute to each term inside of parentheses. That's when distributive property is used. Substitution. This is a really important one. So substitution gets confused with transitive property a lot. Now, in substitution, all we're doing is like replacing a term in a statement. So like we already have a statement written. We know that one of the terms in that statement is equal to a new term. So we can just substitute that in. This is going to be hard to explain. It's just easier if you see it once we work through a few examples here. Let's see here. But again, substitution gets confused with transitive property, so you might want to just keep an eye on those two. Reflexive property is just when you're saying something is equal to itself. This isn't used a lot in this lesson. We're going to be using this in Unit 4 a lot, though, and we'll revisit it then. Symmetric property is basically saying, so this is if A equals B, then B equals A. So the symmetric property is used to basically rewrite things so that they appear the way that you want them. So like, for instance, if we solved an algebraic proof and we got to this step where it says if 12 equals X, and we want our final result, or we want our final proof or final statement to actually say X equals 12, then we can use the symmetric property to swap those around. And then the transitive property, again, this is the one that gets confused with substitution a lot. Basically says that if A equals B and B equals C, then A equals C. So this is not necessarily substituting something in. You're saying that, well, if this thing is equal to this thing, and this thing is also equal to this thing, then the original thing and the third thing have to be equal as well. Again, kind of difficult to understand without seeing some examples, so that's what we're going to do here shortly. Other properties that you need to be aware of are definition of congruence. So definition of congruence is really used when you're switching between an equal sign and a congruent sign. Basically just says that if two figures are congruent, then they have to be equal in measure. Or if they're equal in measure, then they have to be congruent. And we'll see how this works in a little bit. We have definition of midpoint. This property is used whenever they tell you that there's a midpoint. Like if they tell you there's a midpoint somewhere, we're going to use definition of midpoint. It's used when we're saying two segments are congruent because there's a midpoint given, or a midpoint creates two congruent segments. So we can actually maybe write a new statement based off of the given midpoint as well. And then we have definition of bisect. So again, bisect means that we're cutting in half into two congruent parts. So when we use this when segments or angles are bisected. So it allows you to say that two segments or angles that have been bisected are congruent. And we'll see this in use here shortly. And then last couple of ones are segment and angle addition postulate. So we already touched on this. Segment addition postulate is basically saying that if you have two segments, you add them together to make a whole segment. So like in this case, if we have a line where A, B, and C are points on a line with B in the middle, then we know the distance from A to B plus the distance from B to C should be equal to the distance A to C, the whole length of the segment. And it's the same thing with angles here. So the best way to look at proofs is probably just to run through examples. So with example 1, let's start by looking at this proof here. So we're given E is the midpoint of DF. And we're trying to prove that 2 times the length of D to E is the same as the length of D to F. So logically, you should be able to just understand that this is true just by knowing what midpoint means. So like we know that E is the midpoint, so that means that this distance D to E is the same as this distance E to F. So because these distances are the same, then if we just took D to E and multiplied it by 2, it would be the same as that full distance D to F. So logically, you should be able to think through a proof before you even start it. So in this case, if we're looking at this very first statement, E is the midpoint of DF, in our 2-column proof, we know that the reasoning here is because that is the given statement. This information is given to us, so we can just write given there. And now we're just going to interpret what the midpoint means. So if E is the midpoint, then we know that the distance from D to E is equal to the distance from E to F. That's what statement 2 is saying right here. And that's just because that's what the definition of a midpoint is. If E is the midpoint, then these distances have to be the same. They have to be equal. Next up, look at what happened from 2 to 3 here. We have DE equals EF in statement 2. And now we have DE plus DE equals DE plus DEF. So what they did is they added DE to both sides in this equation. So if they're just adding the same term to both sides in the equation, that is addition property of equality because we added DE to both sides. Now, from statement 3 to statement 4, the right-hand side didn't change at all, but my left-hand side, all we did was we simplified this and rewrote DE plus DE as 2DE. So we simplified or combined like terms. Oops. And then number 5. So there are going to be times where number 5 in this particular case doesn't really come from statement 4. It actually comes from looking back at the diagram here. So statement 5 says DE plus EF equals DF. So they're saying that the length of D to E plus the D to E to F has to be equal to the whole length D to F. We know that's true because of the segment addition postulate that says if you add these two segments together, they should equal the whole. Now, what we're left with is we have D to E plus E to F equals D to F. We know that from statement 5. And we should also notice in statement 4 we have d to e plus e to f right here as well. So what we can do is we can actually say with the transitive property, we know that 2de is the same as d to f because that's just the transitive property, because 2de is equal to de plus ef, and then de plus ef is also equal to df, so therefore 2de has to be equal to df. So this is how this proof would be solved here with the transitive property as the last reasoning. All right, let's look at another example, example 2. So example 2, again, if you're familiar with proofs, the very first statement here is what is given. So the reasoning there is just going to be given, so I'm going to write that in first. Statement 1 to 2 is pretty much the same statement, except what they did is they changed the congruency symbols to equal signs. And here we're saying that we have congruent segments. Now we're just saying that the distances between these LM and LN are equal. Same with here. So what we're doing is we're dropping the congruency and going back to equal sign. We know that we can do that because that's what congruent means, is that if they're congruent, they have to be equal in length or distance. Now, next up, we know that KL equals LN, and we also know that LN equals LM. Therefore, we can say that KL equals LM because that's the transitive property. Okay, next up, we know that if KL, so K to L, is equal to L to M, so they're saying that the distance from K to L is equal to the distance from L to M. That means that L is right in the middle, so L is the midpoint of KM because that's what a midpoint is we know it's a midpoint if the segments in between those 2 points are congruent or equal. So statement 3 kind of implies statement 4, and then statement 4 we know is true because that's what a midpoint is. All right, let's look at example 3. Example 3 here. So we have PQ is congruent to TQ. And so again, sometimes when performing these, let me see here. Sometimes when performing these proofs, it is helpful to actually like mark the congruency. So if PQ is congruent to TQ, I can actually put little tick marks on these segments here to show that they're congruent. And UQ is congruent to QS. So I can put 2 different tick marks on them as well. But we'll just go ahead and solve this proof out. So number 1, this is a given statement again, because we're starting off with the given information. Here from 1 to 2, they're dropping the congruency symbol, moving to equal sign. We can do that because the definition of congruence says that these distances have to be equal if they're congruent. Next up, this might be one of the tougher ones. So again, number 3, it looks like we have PQ plus QS equals PS. So why don't you take a look at the diagram. We have P to Q plus Q to S equals P to S. So that is a segment addition postulate. And then TQ plus QU, so T to Q plus Q to U equals TU. That's also segment addition postulate. Now, this is where it gets a little bit even more tricky. So we have this initial statement in number 3 where the segment addition postulates. In number 2, we have this information where we know some things are equal to other things. So in statement 4, we're actually rewriting this first statement right here in statement 3. We're rewriting this, except instead of PQ, we're replacing it with TQ. Because in statement 2, we know that they're equal. So we're taking the TQ, we're plugging it in here. That's substitution. In statement 5, we're manipulating this statement right here. We know that UQ, which is the same as QU, so UQ and QU are the same thing. We know that they're equal to QS, so we can actually substitute the QS in for QU, and that's what we have for statement 5 is we're replacing through substitution. And then in statement 6, we have TQ plus QS equals PS, TQ plus QS equals TU. So if these two things are equal, then PS has to equal TU through transitive property. And then PS is congruent to TU because if they're equal in distance, they have to be congruent as well. So the definition of congruence. Now, we're not going to be able to get through with the remaining time that I have, so I'm just going to kind of go through these ones quick. So we have our given statement, write the given. BE bisects ABD. The definition of bisect tells you 2 things are congruent or 2 angles are congruent. This is also a given statement, so sometimes given statements can come later on. definition of bisect again.